After this video lesson, you are expected to calculate equilibrium constant and the pressure or concentration of reactants or products in an equilibrium mixture. Equilibrium is defined as a state in which there are no observable changes as time goes by. And chemical equilibrium is achieved when the rates of forward and reverse reactions are equal and the concentrations of the reactants and products remain constant. We need to look at two different types of equilibria, homogeneous and heterogeneous separately, because the equilibrium constants are defined differently. A homogeneous equilibrium has everything present in the same phase. The usual examples include reactions where everything is a gas or everything is present in the same solution. A heterogeneous equilibrium has things present in more than one phase. The usual examples include reactions involving solids and gases, or solids and liquids. In writing an expression for Kc for heterogeneous equilibrium, there is no need to include any term for a pure solids or pure liquids in the equilibrium expression because their effective concentrations stay constant throughout the reaction. Consider this general reversible reaction. This means that for the reaction of the reactants referred to as forward reaction, that is A plus B yields C plus D, or rate forward is equal to K forward, A raised to A multiplied by B raised to B. And for the reaction of the products referred to as the reverse reaction, we have C plus D yields A plus B, or rate reverse is equal to K reverse C raised to C multiplied by D raised to D. The opposing reactions will occur simultaneously provided the reactants of both reactions are present. For the opposing reactions at equilibrium at certain temperature, rate forward is equal to rate reverse. Writing the rate law expression for each opposing reaction, assuming the order equals to the stoichiometric coefficient in the balance equation and applying the principles of kinetics, we have K forward A raised to A multiplied by B raised to B is equal to K reverse C raised to C multiplied by D raised to D. Thus, the general expression for the equilibrium constant of the reaction is Kc is equal to products divided by reactants, or equilibrium constant, that is Kc is equal to C raised to C multiplied by D raised to D divided by A raised to A multiplied by B raised to B. Its value indicates the extent to which the reaction proceeds toward completion at the given temperature. Note that although the opposing rates are equal, it does not mean that the concentrations of the product and the reactants are also equal. For instance, the following reversible reaction, which is 2 moles sulfur dioxide gas plus 1 mole oxygen gas, yields 2 moles sulfur trioxide gas. The equilibrium constant expressions is Kc is equal to SO3 raised to 2 divided by SO2 raised to 2 multiplied by O2. The symbol C in Kc indicates that units for the reactants and the products are those in concentration, which is usually in molar concentration. For some equilibrium reactions, the Kc has no units. Let's do mathematical calculations involving Kc. The problem is, Calculate the value of the equilibrium constant Kc for the system shown if 0.1908 moles of carbon dioxide, 0.0908 moles of hydrogen gas, 0.0092 moles of carbon monoxide, and 0.0092 moles of water vapor were present in a 2-liter reaction vessel were present at equilibrium. The equation is 1 mole carbon dioxide gas plus 1 mole hydrogen gas yields 1 mole carbon monoxide gas plus 1 mole water gas. Step 1 is write the equilibrium expression for the reaction system. Take note that Kc is equal to products divided by reactants. Thus, Kc is equal to CO multiplied by H2O divided by CO2 multiplied by H2. For step number 2, express equilibrium amounts to molar concentration. In this example, the amounts are only expressed in number of moles. Thus, conversion of each is required. To get the molar concentration, we just simply divide given moles of components by the volume, which is 2 liters. Thus, for carbon dioxide, the molarity is 0.0954. For hydrogen, it is 0.0454 molar. For carbon monoxide, it is 0.0046 molar. And for water, it is 0.0046 molar. And the final step is substitute its concentration into the equilibrium expression and calculate the value of the equilibrium constant. So, Kc is equal to 0.0046 molar multiplied by 0.0046 molar divided by 0.0954 molar multiplied by 0.0454 molar, and you will get 0.0049 or 4.9 times 10 negative 3. It's time to challenge yourselves by answering this problem. Good luck! Now let's have equilibrium constant Kp. For reactions involving gases, the equilibrium constant is often expressed in terms of partial pressures of gases rather than concentrations. The equilibrium constant is then given the symbol Kp. The partial pressures of gas is related to the number of moles of the gas by the ideal equation PV is equal to nRT, where the value of R is the gas constant, which is equivalent to 0.0821 liter atmosphere per mole Kelvin. P is for pressure, N is for number of moles, and T is temperature. And temperature must be in Kelvin. Let's do mathematical calculations on equilibrium constant Kp. The problem is, the equilibrium constant Kp for the reaction below is 158 atmosphere at 1000 Kelvin. What is the equilibrium pressure of O2 if the pressure NO2 is equal to 0.400 atmosphere and pressure NO is equal to 0.270 atmosphere? The reaction is 2 moles NO2 gas yields 2 moles NO gas plus 1 mole O2 gas. The equilibrium constant Kp is equal to pressure NO raised to 2 multiplied by pressure O2, which are the products, divided by pressure NO2 raised to 2, which is the reactant. Since we are looking for the pressure of oxygen, we have to manipulate the given formula. So we have the formula pressure O2 is equal to Kp multiplied by pressure NO raised to 2 divided by pressure NO2 raised to 2. Substituting the values, we have pressure O2 is equal to 158 atmosphere multiplied by 0.400 atmosphere raised to 2 divided by 0.270 atmosphere raised to 2, and we get 347 atmosphere. In expressing Kc and Kp in heterogeneous system, the concentration of solids and pure liquids are not included in the expression for the equilibrium constant. Since any solid will be constant like CaCO3 and CaO in this reaction, the expression for Kc is equal to CO2 and for Kp is equal to PCO2. This time, let's do conversion of Kc and Kp. Kp is equal to Kc multiplied by RT raised to delta N of gas, where delta N is equal to moles of gaseous products minus moles of gaseous reactants. R is the gas constant, which is equal to 0.0821 liter atmosphere per mole Kelvin. And T is for temperature in Kelvin units. For example, find Kc for the following reaction if Kp is equal to 2.1 times 10 to the negative 4 at 1000 Kelvin. The reversible reaction is CaCO3 solid yields CaO solid plus CO2 gas. The change in number of moles of gas in the reaction is 1 minus 0, which is equal to 1, since there is only a gaseous product and no gaseous reactants. If Kp is equal to Kc multiplied by RT raised to delta N of gas, therefore Kc is equal to Kp divided by RT raised to delta N of gas. Substituting the values, we have Kc is equal to 2.1 times 10 to the negative 4 divided by 0.0821 times 1000 raised to 1, we get 2.6 times 10 to the negative 6. It's time to challenge yourselves by solving this problem. I just do hope that you have learned a lot from this video lesson. Goodbye!